In this lesson, we will be looking at solving systems of equations using inverses as well as Cramer's rule. So these two methods are slightly faster in solving a system compared to a row operations or row reduced echelon form style of problem. It does require us to understand how to find inverse matrices as well as finding determinants, which we covered in the previous lesson. So for 2 by 2 matrices, what we do is we take our 2 by 2 matrix, augmented with the answer column here, and we break it into these three different parts. So we're going to break it into a matrix A, this single column matrix X of variables. That one's really not that important. It's always the same. And then B is going to be our column of answers. So if you look at the coefficients here, the A, B, D, and E become this matrix A over here, which is the coefficients of all of the x's and y's from the original system of equations. And then the column of variables is always just going to be whatever variables you have. So for our 2 by 2, it's x and y. Later we'll see a 3 by 3, and that would be x, y, and z. Then B is going to be another single column, and that's just going to be the answers. So in this case, C and F, whatever those numbers are. So the setup's not too bad. We're just taking these and rewriting them into these three smaller matrices instead of doing one big augmented matrix like we did in the earlier parts of this. So we still are going to be building on the determinants, which we covered again last section. We're going to use that to find a inverse, which is what we finished last set of notes with. So the solutions for the system would be x, the variables, would equal A inverse, the matrix A inverse, times B, which is again our column of answers. So there's a lot of parts here, and it might seem overwhelming to start, but it's really, really simple, and it becomes very quick with a 2 by 2 matrix, since we know the little shortcut for finding a 2 by 2 inverse using the determinant. All right, so we start here. Here's an example. To start matrix A, we're just going to take the four coefficients of the x's and y's and write them in this matrix. So that'll be 2, so it's 2x, minus 3y, so that's negative 3, minus 3x, so it's negative 3, and then plus 5y. So there we go. As you'll see, that x column is always just the variables, so I already went ahead and filled that in. And B is the answers, so negative 1 and 3. So that's the setup. We take the coefficients from the system and we make them A, and then the solutions become matrix B. Then we need to find the determinant of A, and that is pretty quick when it's a 2 by 2. So again, we do the cross products and we subtract them. So we have 2 times 5 minus negative 3 times negative 3. 2 times 5 is 10 minus negative times a negative, so positive 9. So the determinant of A is just 1. So this is going to be a really easy one. Remember that the inverse of A is always going to be 1 over the determinant. Then we are going to switch, if it was A, B, C, D, we would switch the two values there and then change these to the opposite sign. So D, negative B, negative C, A. So for the A we started out with, be 1 over the determinant we just found, so 1 over 1. We're going to switch the 2 and the 5, and then we're going to change the sign of both of the 3's. And we end up with just that 5, 3, 3, 2. Okay, so that is the inverse of A. Pretty quick on this one. To find our answers, we're now going to do some matrix multiplication. We're going to take the A inverse we just found, so 5, 3, 3, 2, and multiply it to the solution column, which was negative 1, 3. When you get to this point, the multiplication should always work. If it doesn't, it means you've really, really messed up somewhere, because it should always be a 2 by 2 times a 2 by 1. So the internal dimensions should agree. If you've done something incorrect, and the multiplication doesn't work, you're way off, go back, try that again. But what we have here is rows to columns, so the 5 goes to the -1, and the 3 goes with the 3, so we should end up with 5 times -1 plus 3 times 3. Okay, so that's going to be our first answer there. And then we will have 3 times -1 plus 2 times 3. So we end up with -5 plus 9 and -3 plus 6. So our solutions should be 4, 3. So that is our set of answers now, and we compare it to that column X, which means the top answer is our X answer and the bottom answer is our Y answer. If you want to verify these to make sure, it'd be a good idea to take these two values, X equals 4 and Y equals 3, and plug them back into the original equations. That's a great way to check. So if we do that quickly here, we should get 2 times 4 minus 3 times 3 equals -1. I believe it does. And then 3 times, -3, sorry, times 4 plus 5 times 3, and that should equal 3. So in that top row, we get 8 minus 9, and that in fact does equal -1. On the bottom row, we get -12 plus 15, and yes, that does equal 3. So those solutions are correct. It might seem like more work, more writing, but it avoids the row operations, which can get a little bit tricky sometimes if there are fractions and things like that. So this is potentially a quicker way to solve these systems of equations. Down below here, we've got another example. If you would like to pause the video at this time and take a moment to do that, I would strongly encourage it. Okay, so hopefully you've got it figured out, and we're going to go through here and see if we can find the solutions for this x and y. Again, we're going to start this problem out by creating the matrix A, which is the coefficients of the x's and y's. So we have 6, 1, -4, -5. Column X is always going to be X and Y. I'm not going to bother writing that down. And then the matrix B is going to be the two solutions, so -8 and -12. Okay. So the next step we want to do is to find the determinant of A. So the determinant of A here would be 6 times -5 minus -4 times 1. Okay, so we're definitely going to get a determinant that's not 1. So 6 times -5, that's -30, minus -4 times 1, that is -4. So we end up with -26. So our inverse, we will have 1 over the determinant times, and then we're going to rearrange our matrix, so -5, -1, +4 there, and 6. Okay, so we get to this point and we're like, we got that fraction, -126, that's not pretty with all those numbers. Really don't want to put that in there. It's going to make things a little bit messy. That's totally fine. What we can do with our properties of matrices, this 126 can kind of just hang out on the outside. So we can do 1 -26 of that matrix A, -5, -1, 4, 6, and multiply that to column B, -8, -12, and then we can bring this back in at the very end. So that's what I'm going to do. I'm going to hold off on that until the very end and see what happens with our multiplication first. So this is just tagging along for the ride right now. And we are going to do our multiplication. So we have 5 times -8 plus -1 times -12 And then for the second, we've got 4 times negative 8 plus 6 times negative 12. So we're still going to have that 1/26th out front. 5 and 8 is 40. Negative 1 or negative 12, that is 12. And then we've got negative 32. 6 times negative 12 is negative 72. Okay, so we still have this negative 1/26th out here. We're going to add these together so we get 52, and we get negative 104. Okay, so at this point, looking at these two numbers, it's really a smart thing that we didn't do that 1/26th earlier, because 104 and 52 are both divisible by 26. They're divisible cleanly by 26. So by waiting and holding off, we don't have to deal with fractions really at all in this problem. We just have these numbers at the end, multiplying by the 1/26th, and we are good to go. If we brought it in earlier, we'd have 5/26. That's not a pretty number. That's not as easy to work with. So wait until the end, and then hopefully things work out cleanly as like whole numbers or easier fractions, half, a third, fourth, something like that. And for this problem, it absolutely does. So 52 divided by negative 26, that is going to give us negative 2. And then 104 divided by 26, that is 4. Okay, so those are really nice solutions. Again, whole number solutions like we got in the first example. So we're going to go ahead and plug these in, just make sure they work. So x was negative 2 and y equals 4. So if we do 6 times negative 2 plus 4, that is negative 12 plus 4, which is negative 8. Great. And then we have negative 4 times negative 2 minus 5 times 4, which is 8 minus 20, which is indeed negative 12. Great. Okay, so both of those worked out, and we got our solution at negative 2, 4. Okay, so now we're going to move on to 3x3 matrices, and unfortunately, since 3x3 matrices are a little bit bigger, it's not as quick of a process to do the 3x3s. Finding a 3x3 inverse is a little bit more involved. We don't really have a determinant method with switching things around. You would have to use the row reducing to find that inverse matrix. And if you're doing the row reducing to find an inverse, there's really no point to doing that and then going through a solution like we've just done. If you're going to do row reducing, you might as well make it an augmented matrix and just do the row reducing to find a solution. So this method, though, which is called Cramer's rule, helps us find a solution quicker than doing row operations, and it does not involve an inverse. We still use a determinant, so it's still in the same ballpark of using a determinant first, but we do not need to actually find the inverse, which is good because, again, 3x3 inverse is a little bit more challenging to find. So the only caveat here is it must be a square system, so it has to be a 3 equations, 3 variables. We can't have 4 equations, 3 variables. That won't work for us. It has to be the same number of variables and equations. Okay, so before we really get into this, which there's a lot going on here, and it's not difficult. There's just little, again, pieces that are moving around, kind of like the first example where there's a lot of setup, small little details for setup, and then the work is not too bad. I want to go back to the previous section where we looked at finding the determinant of a 3x3, and we found, I believe this one was 32 or negative 32. We'll verify that here in a second, but that process that we used to find this determinant was a little bit less efficient than it could be, I guess. What we did was we blocked out the columns and we multiplied the first element to the resulting leftover matrix when we blocked out the column. And that works and it's great and it gives us our answer, our determinant. But there's a slightly quicker, in my book, method to doing this that I'm going to show you right now. So what we want to do is we want to recopy this matrix. And then we want to put another copy of the same matrix directly on the other side of it. So again, just repeat these elements. So what we're going to do is we are going to do the diagonals like we did for a 2 by 2, now for a 3 by 3. So we need this extra copy so we can make our diagonals. Our diagonals all have to have 3 elements in them. So if we didn't make this copy, it wouldn't work. So what we're going to do is we're going to start in the top left corner, just like we did for the other one, and we are going to go down the diagonal. So these 3 elements together. So that'd be -3 times -1 times 0. And then we're going to move to the next, which is the 2, and we're going to go down that diagonal. So we've got 2 times -1. And then our last diagonal here is 4, 1, 4. Okay, so there's 3 diagonals going that way. Then what we're going to do is we're going to go the other diagonals, starting at the 3 and going backwards. So we go this -3 and we go backwards that way. So that's -3 times 2 times 4. And then we go to the 2, so 2, 1, 0. And then the 4, -1, -1. Okay, so we've got these sets of diagonals. We've got now 6 numbers to multiply, and the 2 by 2, we had the difference of the 2 diagonals. What we're going to have here, since we've got a lot more diagonals, is the first 3 that we did. So starting at the 3, the 2, and the 4, those are all going to be positive. So this is positive, positive, and positive. Then the second set of 3 that we did, starting at this -3, 2, 4 for the second time, those are all going to be negative. So the first 3 we did are positive, the second 3 we did are negative. So let's take a look and see what we get when we multiply all this out and add it together. So this first set of products here is going to be a 0 because there's a 0 there. The second set of products, so plus 2 times 2 times -1, that is -4. And then this third set of products, it's 4 times 1 times 4, so 16. Okay. Now we're moving on to the minus parts. So we've got minus -3 times 2, which is -6. -6 times 4 is -24. Minus, this one is going to be a 0 since there's a 0 there. And then minus, we've got 4 times -1 times -1. So -4, +4. Okay. Now I'm just going to distribute these signs. So this will become 0 plus -4 plus 16 plus 24 minus 0 minus 4. And if we put all this together, we should get, right there is a 40. That's a -4, -4, so 8. And we end up with 32 as we did the last time we did it, which is good. So we now have this alternate method of doing 3 by 3 determinants, which is pretty nice. And I'm going to use that today to do what we're about to do, rather than doing the blocking out of the rows. If that method works for you, if you like blocking out the rows, go for it. It will give us exactly what we need for the example we're about to try. But I want to use this newer method. I think it's a little bit quicker, and I'm all about saving time. Okay, so to do Cramer's rule, what we're going to do is for matrix A, that's an n by n matrix, so we don't put the answer column in. We just do the 3 rows and the 3 coefficients for x, y, and z, such that ax equals b, which is the same setup we just looked at. Determinant of a can't be 0, so that is something we have to determine. Then the solutions to the systems are the determinant of a1, we'll talk about what that is, divided by the determinant of a. That's your first solution, and then so on and so forth. Second solution, third solution, until you're finished. That a sub whatever number it is found by replacing the ith, column of a with the column of constants, the answer constants, b. So what we're going to do is replace the first column of a with the answers, and then do a determinant, and then replace the second column of A with the answers, and then do another determinant. And that's going to give us all of our answers. So here's how the process works. And for a 2 by 2, it's really quick. And it's actually a really, I I think this is actually the easiest method of finding the solutions. It's the least kind of work, especially for a 2 by 2. So here, what we're going to do, now notice they've changed the variables to x1 and x2. It makes no difference. If you're more comfortable with xy, just change it to being x and y. So we rewrite the coefficients, okay? And then we're going to define the determinant using the method that we've done with the cross. So we have 3 times negative 1 minus negative 4 times 2. So that is going to be negative 3 minus negative 8, which will be 5. Okay, now here's where the fun comes in. What we're going to do now, since this is a sub 1, we're going to replace the first column, which would be 3, negative 4, with the two answers. So this first column, instead of being the 3, negative 4 that we just did, is now going to be these two answers. So 6, negative 13. So we replace the first column with the answer column. The second column stays the same, so 2 and negative 1. And then we're going to do the same process to find the determinant. Do the cross products here. So 6 times negative 1 minus negative 13 times 2. So 6 times negative 1 is negative 6 minus 13 times negative 2 is negative 26. And we end up with negative 6 plus 26, which is 20. And that's really good for us because our original determinant was 5. 20 is divisible cleanly by 5, so we are in good shape. They don't have to work out cleanly, but for these examples, they usually do because they're just kind of getting us started and they want to give us nice, easy answers. All right, so we're going to do the same process again. This time, though, we're going to replace column 2. So instead of having a 2 and negative 1 in the second column, we're going to replace that with our answers, 6 and negative 13. So column 1 is back to 3 and negative 4. And then column 2 is now 6 and negative 13. Same process again, we take the determinant, so the crosses here, we have 3 times negative 13 minus negative 4 times 6. 3 times negative 13 is negative 39 minus 4 and 6 is negative 24. So we end up with negative 39 plus 24, and that will be negative 15, which again is divisible by 5, so we are in good shape. To finish this out, we're going to take those numbers we just found, and we're going to fill them into these two fractions here. So this is the determinant of a sub 1, so the first one that we replaced. So that number was 20, divided by the determinant of the original, which was 5. And 20 divided by 5, that's a nice easy solution of 4. Then we go on to the next one. So the determinant of a sub 2, which was the second one we did, we found that to be negative 15 over the original determinant, which was 5, which gives us an answer of negative 3. Okay. So we've got our answers, and we can always go back and check them. So 3 times 4 plus 2 times negative 3, that is 12, minus 6, which is 6, good. And then negative 4 times 4 minus negative 3, which is negative 16 plus 3, which is negative 13. Awesome. Okay, so those are the solutions. We've got them. This process, again, is a little bit heavy on the legwork, but once you get it set up, it's really quick determinants. Once you understand the process of replacing the individual columns, it is probably the quickest solution method we've got. So there are two more examples down here, and take a go at them using this new determinant method, Cramer's rule. Go ahead and pause the video and try those now. So for this first one, we're going to start by just writing out what matrix A is. So A is negative 9, 3, 2, negative 1. And we're going to find the determinant of that. So we'll have negative 9 times negative 1 minus 2 times 3. So that is 9 minus 6, which is 3. All right, so now we're going to start replacing. That again is the determinant of A. So for A1, A sub 1, we're going to replace the first column, so the 9 and the 2 are going to be replaced by 8 and 3. So it is now 8, negative 3, 3, negative 1. Same process, 8 times negative 1 minus negative 3 times 3. So that's negative 8 minus negative 9, which is 1. For A2, this goes back to the original, so 9 and 2. And then the second column becomes 8, negative 3. So the determinant here, we have negative 9 times negative 3 minus 2 times 8. So we get 27 minus 16, which is 11. So not pretty answers it's going to look like here, but that's okay. They don't have to be nice. Just mentioned that they were starting us off with something easy, but now they've kind of kicked it up a little bit. So x is going to be determinant of A1 divided by the determinant of A, and y is going to be the determinant of A2 divided by the determinant of A. So here we'd have 1 over 3, and here we'd have 11 over 3. Okay, so let's verify because those are not pretty numbers and just want to make sure. So we have negative 9 times 1/3 plus 3 times 11/3. So 1/3 of negative 9, that's negative 3. And 3 times 11/3, that's going to be 11. And negative 3 and 11 makes 8. Okay, good. Then we have 2 times 1/3 plus, minus really, minus 11/3. So we're going to end up with 2/3 minus 11/3, and that is negative 9/3, which is negative 3. Okay, we're in good shape. So even though they were thirds, still viable answers. So don't be alarmed if you get some fractions. Again, thirds, fourths, those are normal fractions. If you're getting like 17ths, you might be in a little bit of a bad place there, but once you get your answers, check them. If they worked out and they're correct, then you're good to go. Second example here, so we'll start the same way. We'll start with A, and that is 12, negative 9, 4, negative 3. We'll find the determinant of that. So we have the 12 times negative 3 and 4 times negative 9. So 12 times negative 3, that is negative 36 minus negative 36. And hopefully we're finding 0. All right, so at this point, if you went on and did other work, okay, hopefully eventually you realized that something was off with this problem. So the determinant of A is 0. So when we go to do this step, divided by the original determinant, what will happen is we'll have some sort of value dividing by 0. That's no. We can't divide by 0. And if you go back to the original statements up here, this, if the determinant of A does not equal 0, that's what gives us a problem. We cannot have the determinant of A equal 0. If it does, we will not be able to do this process. We will not be able to use the division because we can't divide by 0, so Cramer's rule does not work. If the determinant of A is equal to 0, we also saw in the previous section that that meant it had no inverse. which is what we talked about right here. If the determinant of A equals 0, there is no inverse. So really, when we have this determinant of A equaling 0, there's not a lot we can do with that problem. So if we do run up against that, it's kind of the end of the problem. There's no inverse. There is no way to kind of solve it like that. And really what's happening here, and I don't think we've talked about it before, these two lines are parallel, which means they're never going to intersect. If we would solve these for like slope-intercept form, get them into mx plus b, we would see they have the same slope but different intercepts, so they actually never intersect. So there is no solution for these two equations. Or they could be the exact same, which has all solutions. That can happen sometimes too, but for this one specifically, if we would divide this top one by 3, you would get the exact same thing as the bottom. You'd have 4x minus 3y, but you'd have a different intercept, negative 5/3. So these are parallel lines, no intersection, which means no solution. Okay, so that can happen if your determinant is 0. The answer is no solution. Okay, so the last one we have here is a 3x3, and not really sure what's going on with this minus and negative 4z here, so we'll see what happens with this problem. Hopefully it works out, but whenever we've got this 3x3, we can still use the Cramer's rule. I'm actually going to take just a second here and check this because we've also got this 1 in the bottom. So I'm going to go find this problem, check it out, and be right back. Okay, so there was just a little bit of an error here. So this is actually an equal sign, and that 1 is supposed to be there. So the example that they gave us here is not written in standard form for all of the equations. So that's part of the process here is they want us to get this into standard form first before we start doing matrices. So that was a little error there. Make sure that's an equal sign. Negative x minus 2y equals negative 4z plus 12. Okay, so we do want to get this into standard form. So the letter parts need to be on the left. The just constant plain numbers need to be on the right. So we'll rewrite that. I'm not going to do a matrix yet. So we have negative x minus 2y. So that becomes plus 4z equal 12. Then we have 3 minus 6, 3x minus 6y plus z equals 15. So that row is fine. We didn't have to do anything there. And then we need to get that 1 off the other side. So we have 2x plus 5y plus 0z. So I'm going to leave a placeholder there so I don't forget, equals negative 1. Okay, so start by getting this into standard form for all of the equations. Make sure that they are ready to be made into a matrix, and then go ahead and make that matrix. So we have negative 1, negative 2, 4. We're not using the answers here. We're going to move that off to the side. 3, negative 6, 1, 2, 5, 0. So that is our matrix A. And then our answer column is 12, 15, negative 1. So we are going to put that into the different columns as we go through this. As I mentioned before, the other way of doing the 3x3 determinant with the rewriting it, second copy, and making the diagonals, that's the way I'm going to do it today. If that didn't make enough sense to you, or if you're a little shaky on it, or just want to do the first way you learned because that's what you figured out how to do, by all means do that. I'm going to do it the diagonal way. So I'm going to take my A to find the determinant and copy another one next to it. Okay, and then I'm going to make my diagonals. So we've got negative 1 times 6 times 0, so that one is going to be 0. Negative 2 times 1 times 2, so that is negative 4. And then 4 times 3 times 5, it's going to be 20 times 3, so 60. And those are all positives. And then I'm going to go the other direction, and they're going to be negatives. So 5 times 5 times negative 1 is negative 5. And then this one is going to be 0. And then we're going to have negative, getting a little tight in there, sorry, 4 times 6, which is negative 24, times 2 is negative 48. Okay, so negative negative 5, so that's positive 5, plus 0, negative negative 48, so plus 48, minus 4, plus 60. Okay, that's going to be a big number there. So we've got, that's 44, so 60, 44, and 5, 109. Okay, so we'll work through this. We are actually going to get some pretty large numbers on the replacing as well. So hopefully they're all divisible by 109. So when we do A1, we are going to replace the first column with these answers. So 12, 15, negative 1, negative 2, 4, negative 6, 1, 5, 0. Okay, so I'm going to write that copied next to itself. Kind of put a big divider here. So 12, negative 2, 4, 12, negative 2, 4. Space this one out a little bit so we don't get as crammed, especially with these bigger numbers. 1, 15, negative 6, 1, negative 1, 5, 0, negative 1, 5, 0. Okay, so we're going to do the cross or the diagonals again. So 12 and 6, that is negative 72. 2 times 1 times 1, that's going to be positive 2. 4 times 15 is 20, so that is going to be 300, positive 300. Okay, now we're getting big numbers, which is good because we have 109 and we need things to be divisible by 109. So the other diagonals are going to be negative now. So we do this first one here. And we get 5. I'm going to write it all the way over there, negative 5. Oh, so that's a 12. Okay, so negative 60. That's 12 times 1 times 5. So then that's a 0 for this next one since it's going through the 0. And then we have 4 times negative 6, so negative 24 times negative 1, so positive 24, but then all of these are opposite signs, so negative 24. So we've got 300 plus 2 minus 72 plus, minus 24 minus 60. So I'm going to take a second and calculate that out. So 300 minus 2, no, 300 plus 2, so 302 minus 72 minus 24 minus 60, which is 146. Uh-oh, we're not in good shape here. And we're not in good shape because I did bad multiplication. If you look back at the 12 times 6 times 0 there, that's not 72, that should be 0. So it does not work if you do bad multiplication. So that is a 0, which means that part is gone. So if we add 72 to that, we should get, I think, 218. Okay, which is much better because 218 is divisible by 109. So A1 divided by A, we would get 218 divided by 109, which is 2. Okay, so again, they're giving us an example here. If it's a crazy, that's a crazy fraction, like 124 or whatever it was divided by 109. That's a crazy not reducing fraction. So that should be a red flag that something's wrong. Go back and check your work. I found my mistake, fortunately, and we're moving on. Okay, so for now A2, we replace the middle column. So the original column 1, the answer column in the middle here, so 12, 15, negative 1, and then the third column 410. Okay. So we start off by recopying negative 1, 12, 4, negative 1, 12, 4, 3, 15, 1, 3, 15, 1, 2, negative 1, 0, 2, negative 1, 0. Okay, so we're going to do multiplication correct this time, and that one's going to be a 0. 12 times 1 times 2 is 24, and 4, 3, and negative 1 makes negative 12. 1 times 1 times 1, so that's 1. Positive 1, so that becomes negative since we're doing this as subtraction. 12, 3, and 0 is 0, and 30 times 4 is 120, and that becomes negative, so negative 120. So we have negative 120, negative 12, and negative 1, so that's negative 133 plus 24, so that should be negative 109. So A2 divided by A is negative 109 divided by 109, which is negative 1. Again, should work out for us pretty cleanly here. We shouldn't be getting anything funky. So negative 109 gives us a solution of negative 1, so that's good. Okay, and now for the third, so we're going back to the original first and second column now. So negative 1, 3, 2, negative 2, negative 6, 5, and then we're replacing this third column, 12, 15, negative 1. So we have no more 0 in there, so it's not going to throw us off, hopefully. Rewrite and copy 12, negative 1, negative 2, 12, 3, negative 6, 15, 3, negative 6, 15, 2, 5, negative 1, 2, 5, negative 1. Okay, so these are going to be slightly bigger products this time, again, since there's no 0, and we've got the biggest sets of coefficients, I guess, so we'll see what happens. 1 times 1 times 6, that is 6, but it is negative, 3 negatives. 4 times 15, which is going to be negative 60. And then 12 times 3 times 5. Break out the calculator on that one. So 180, positive. Then we're going to do 5 times 15, so 75, negative 75, but we're doing the opposite sign, so it's going to be positive 75. 3 times 2 times 1, so that's positive 6, but make it negative. And then 2 times 6 times 12, which is going to be 144. It would be negative 144, but we'll make it positive because we want opposite sign. So we should be adding together 75 minus 6 plus 144 minus 6 minus 60 plus 180, which should give us 327. So we have 327 divided by 109, which is, again, a nice whole number, so 3. So we have found our 3 solutions. So I'm going to copy all this back up here, which means that our x answer, which is the first answer we found, was 2. The y answer that we just found was negative 1. And the z answer, the final, was 3. Okay, is that quicker than row reducing? Probably not. Probably not quicker than row reducing for a 3x3. There's a lot of arithmetic to do there, just like the row reducing was. So take it as you will. If you get good at finding these determinants, doing either method, that could be a viable way to solve these, but it does get a little consuming, and if you make a mistake, you can really, really throw your problem off like I did. So there's one more example here using the 3x3 with Cramer's method. So if you want to take a go at this using Cramer's method, finding all the determinants and then dividing them, go ahead and do that at this time. If you want to try it using row reducing, go for it and see if your answers match up, or if you want to try both and see if you get the same thing, that could also be a great time to practice and see which one you would prefer. So either way you choose to do it, go ahead and pause the video now and give this last one a try. Okay, so just like the previous example, we do want to start this one by first writing it into kind of standardized form. The only real problem here is it's missing a z term on this bottom like our previous was, so just put a placeholder 0 there, which means our original matrix A is -2, 4, -1. We're not putting the answer column in yet. 3, 1, 2, and then 1, -3, 0. So we'll start this problem out the same way we did the previous by finding the determinant of A, and I'm going to give it another try using the copying method and doing the diagonals again. We'll see if I can get them all correct this time without any mistakes. Okay, so we do have a 0 again, so I'm going to be wary of that. That means this first one is 0. 4 times 2 is 8, and -1 times 3 times -3 is 9. So those are all positive. Then we go backwards, so 2 times 2 is 4 times 3 is 12. Negative, negative, but make the whole thing negative, so it is -12. 4 times 3 times 0, and we've got -1 times 1 times 1, so -1, but make it the opposite sign, so +1. So we have 9 plus 8 plus 1 minus 12. So we have 18 minus 12, which is 6. Hey, that is a much more manageable determinant this time, and we should feel a little bit more confident in what we're about to do since it's not some crazy determinant like 109. For A1, we are going to replace the first column with our solutions. So instead of the -2, 3, 1, we're going to have 3, -3, sorry, 6, 1, and then 4, -1, 1, 2, -3, 0. Great. And then for the determinant of that, I'm going to recopy, so -3, 4, -1, -3, 4, -1, 6, 1, 2, 6, 1, 2, 1, -3, 0, 1, -3, 0. First diagonal is 0, second diagonal is 8, third diagonal is 18. Those are all positive. So 3 times 2 times 3, that is going to be 18. It's positive 18, but we want the opposite sign, so -18. That one's got a 0. And then the 1 times 1 times 1, but make it the opposite, so +1. So we have 8 and 18. Sorry, 18 and 18. So those are going to reduce to be 0 there. So we will get 9. So it's not going to give us a whole number answer here, but that is okay. We're still getting a sort of fraction that over 6 that works out. So that is 3 halves, which is not a bad number. 3 halves, that is a plausible fraction. So we go on to A2. So the first row, or sorry, first column is back to normal. So that should be -2, 3, 1. The second column, no, sorry, yeah, the second column is now -3, 6, 1, and the third column is still -1, 2, 0. So to do the determinant, we will rewrite that. Double copy, 3, -1, -2, -3, -1, 3, 6, 2, 3, 6, 2, 1, 1, 0, 1, 1, 0. Do our diagonals. So this first one is 0, 3, 2, 1, so that's -6, and then 1, 1, 3, so that is -3. 2 times 2 times 1, that is 4, opposite sign, so +4, that's a 0 again. And 1 times 6 times 1, opposite sign, so that is a +6. So those reduce, and we get 4 minus 3, so 1. So we get 1/6. Okay, and then we're going to go and write out A3. So A3, we're going to replace the third column now. So this is still 2, 3, 1. This third column is going to be -3, 6, 1. I forgot what the middle column should be. The middle column should be 4, 1, -3. Okay, so no 0 this time, so we're going to have to do all of the multiplication. That's okay. So A3, we will double copy, so -2, 4, -3, -2, 4, -3, 3, 1, 6, 3, 1, 6, 1, -3, 1, 1, -3, 1. All right, here we go. So that is -2. That is +24. That is +27. That is -36. 12, but we're going to make it the opposite sign, so -12. And -3, so +3. So we have 27 plus 24 minus 2 plus 3 minus 12 minus 36. So let's see what we get there. 27 plus 24 minus 2 plus 3 minus 12 minus 36. We end up with 4. All right, so A3 over A is 4 over 6, which is 2/3. Again, another fraction, but another nice fraction, if you will. So these fractions are all sort of feasible, reasonable. They aren't anything crazy like 124 109ths. So they are most likely correct, and they are correct. Double checked already. So those are 3 answers. Our x solution was the first one we found, which was 9/6 or 3/2. The y solution was the second one we found, which was 1/6. And the z solution is what we just found, which was 4/6 or 2/3. So those would have been maybe a little more challenging to get with the row reducing since they were fractions. You would have fractions at some point in the problem. That one might have been easiest just going to row echelon form. Who knows? If you did it the other way, you hopefully sort of saw which one worked better for you, which one made more sense. Maybe one of them gave you the correct answer. One of them did not because you made a mistake somewhere. So whatever way is easier or more reliable or quicker, as long as it's producing good solutions, I would suggest using that one because we do want to use the most efficient and most reliable for us. So find a method that works for you. There are multiple ways to do this. There are more efficient ways for some people than for others. And as long as you're getting a correct answer, though, whatever way is most comfortable is the way that I would suggest. So I know that was a lot of arithmetic, a lot of work, a lot of space taken up, but it is a pretty hefty process here for finding these solutions using Cramer's. What I would say, just to kind of wrap this up, is I would use Cramer's more for a 2x2 system. I know that there are other methods that work a lot faster, so really, Cramer's maybe not the most useful thing. The 3x3, it's kind of cool to see that. It's kind of cool to do those determinants, those big determinants like that. But again, the row reducing is probably a little bit quicker than doing a big 3x3 system using Cramer's method. So maybe in retrospect, Cramer's might not be your favorite, might not be the method you choose, but it is another viable option for solving these systems by hand.